Having now gone through some detailed examples of finding the electric field from finite charge distributions and recognizing that mathematically it can be a little bit cumbersome, we're going to discover Gauss's law, which is going to make our lives a lot easier and enable us to solve the electric field from special geometries. That's going to be real simple, where otherwise it would be, well, much more difficult. So let's enter into that simplification process. Let's start by reviewing some of the E-fields produced by finite charge distributions that we've already analyzed. So we have the E-field from a point at point P. That E-field is kq over d squared. If it's a collection of points, then you just add up all the E-fields as vectors. Very simple. Now, the E-field from a line, a finite line. And we had the special condition where the point that we're interested in for the E-field is right in the center of that finite distribution along that line. All right, so the E-field has no y component in that case, and it was kq over x squared of x squared plus a squared. This is something that we seldom have to deal with quantitatively in AP Physics. If we extend that finite line to an infinite line, things got a lot simpler. And it was 1 over 2 pi epsilon 0 lambda over x. That is something that comes up quite frequently. And then the E-field of a ring, different than a line. This is finite, but it had really nice symmetry characteristics where every piece around the entire circle, every dq, contributes to the E-field at this location. So when we integrated around the entire ring, we had, if you integrate all the dq's, you get q, and each one is contributing equally at point P. So we discovered that this was the electric field produced. Looks a little bit different than the finite line. You can see some differences there. And also, we had the electric field of a disk, a finite disk of radius a. The electric field, kind of similar to a ring of charge, but in infinite concentric infinitesimal rings. And that's the result we got. A little bit cumbersome. A little bit non-user friendly. You don't have to memorize that, by the way. Then we had the sheet of charge, which is basically the same thing as taking this disk and sending it out to infinity. And this reduced a lot. In fact, this whole thing, if you remember, actually goes away. And the sheet is sigma over 2 epsilon 0. Something to commit to memory there. And then we discussed dipoles. So an electric dipole in an electric field, E, looking like this. Now torque is P cross E, where P is the electric dipole moment, QD times E sine of theta. The work done by the electric field in rotating the dipole through two different angles from theta 1 to theta 2 is given as follows in the negative sign here. Well, keeping in mind that theta 1 is bigger than theta 2 because this is rotating it to smaller angles, kind of like pushing something in the negative direction. So this inner row will evaluate to negative, and the work done will be positive work by the electric field. And then the potential energy itself is just minus P dot E, which is minus QD, E cosine of theta. And now let's work our way toward defining Gauss's law. Gauss. New important term is electric flux. You've heard of the flux capacitor? Well, I can tell you what a flux capacitor is. I will let you in on that deep ancient secret momentarily, and that moment has come now. Electric flux is E field times surface area. So if I would hold up a hula hoop, and if you imagine wind being perpendicular to that hula hoop. So the wind is flowing directly through the hula hoop. The intensity of the wind times the area of that hula hoop is the wind flux. So flux is intensity, that'd be E field, times area. That's all flux is. So a flux capacitor is just a device that has E field across an area. So it's a flux capacitor. Anyway, sort of diminish your high and lofty view of that regular, somewhat mundane concept. But the net flux in or out depends on the sign of the enclosed charge. That's one of the characteristics. So we have a net flux. It may be zero. But if we enclose a charge, we will have a net flux. And it's proportional to the net charge enclosed. Example, here we have a cube. Let's put the positive charge inside caused an E field to emanate out in all these different directions. And so we have a net flux piercing the surface that's going out of the surface. More flux is going out than is going in. In fact, there is none going in. So it's all going out. An external charge will not produce any net flux. See that? So any flux that goes in, an E field line, okay, that goes in eventually comes back out. So if it's the region of space is not enclosing a charge, there's no net flux. Now, more on electric flux. Phi sub E is equal to EA. So phi is the symbol for flux, sub E electric, E field times area. Check this out. Here's a flat sheet element. Electric field is coming in.
Perpendicular.
Piercing going through. And there's a perpendicular direction to that. E field is perpendicular to the area itself. Now, A is the area. Now, if we tilt it on its side, bring the electric field in, pierces.
Perpendicular.
Angle phi
Perpendicular.
is the direction of the area, perpendicular to the area, and then the angle between the electric field and that perpendicular area is phi. So here's area. Now, this is a vector. This is actually called an area vector, or the vector area. A little bit different than just surface area. Its magnitude is the surface area, but its direction is perpendicular to the area. So when I say area, I just mean the green sheet here, okay? In the geometry of space that it's in. Well, the geometry within the space that it's in. How's that? But the area vector is perpendicular to that area. Make sense? Good. Now, electric flux is EA cosine of phi. So we can multiply the total area, basically this green area times the cosine of this angle gives you the amount of this area that's perpendicular to the electric field. There you go. Now, if the E field is parallel to the area, if it's parallel to it, then there is no flux. But if it's perpendicular to it, then the flux is E times A. And so we have that the electric flux going through an area is the electric field vector dotted with the area vector, E dot A. And this is under the consideration of a uniform E field and a flat surface. That's what we just imposed this analysis on. So a quick example of electric flux through a surface. We have a disk tilted at 30 degrees. The radius of the disk is 0.1 meters. The electric field flows through it horizontally here. So the normal vector, normal of the surface, is 30 degrees. We define the vector area as the vector area is the regular area times the normal unit vector. So that's the unit vector directed outward from a closed surface. Now in this case, it's not really a closed surface, but The normal is directed outward from surface. In that case, the product is going to be positive. We have an E field in the direction, at least partial direction, of that area vector. So the flux, EA cosine of phi. 2000 pi r squared cosine of phi. 54 Newton meters squared per coulomb. That was pretty simple. Let's now generalize this a little bit more. And we're going to have a varying electric field and a varying A, or area. So it's going to be our potato of AP Physics. And there it is, direct to you from the ground. And here's our electric field passing through it. And this is a very complex surface.
A little area element. A little area element.
Indeed, those are differential area elements, each one having its unique differential shape. As you put these little infinitesimal patches over the whole surface, every one is unique. So, what is that going to do for us? Well, each one has its normal direction. So I'm putting a normal vector here on each one. And for the angle between that normal and the electric field is our phi, which changes for each one across the entire surface area of this potato. So picking this one, we have a differential area here. Notice dA, it's a vector differential area. In the direction perpendicular to the area element, size is this differential quantity of area. Now the electric flux through the potato is integral of E cosine of phi dA. Basically the flux, integrating the flux through each little area patch, the electric field times that area. So simplified, that's integral of E perpendicular dA. And what that gives us then is the essence of Gauss's law, namely that the electric flux through a closed surface, which I'll get to some more, is the integral of E dot dA. If you add up all the vector E fields dotted with the area, little area element, if you integrate all those around the entire surface of the potato, you get the total electric flux through the potato. Okay, before moving on, let's do a quick example utilizing this new concept of total flux through a surface. We got a cube, and we have all these normal vectors coming off the various sides. It's in a uniform E field, which is perpendicular to the left face there of the cube. Let's determine the flux through each side and the total flux through the cube. Well, the flux through face 1, right here, let's apply the formula. It's E dot A, which is E dot surface area size, that's A, times the normal, unit vector normal. Well, that's E, L squared is the area. This normal vector is pointing exactly the opposite direction of the electric field, so its angle is 180, so cosine of 180. That gives us minus EL squared. That is the flux through surface 1, the electric flux. It's negative. In surface through surface 2, over on this side, EL squared cosine of 0 is EL squared. So that's positive flux. Now, flux through surface 3, it's going out the back side there, plus 4, it's coming out the front side. Flux through surface 5, the top, and then the bottom, 6, is all the same thing. It's EL squared cosine of 90 degrees between the direction of the electric field and the normal vector in each one of those cases. Every one of those other cases, 90 degrees.
Wow.
No flux. So the total flux enclosed, add them up. And there is 0 electric flux through the surface, which is consistent with there not being any charge enclosed by this sphere. The electric field is external. All the flux that goes in likewise comes out.